your talk.
Okay, great. Thank you for having me, everyone, and for coming today for my talk. So I'll be talking a bit about what we've done in the Gaia group about the 3D structure of galactic molecular clouds, but also then expanding our method out to the full Milky Way as well. I have a bunch of amazing collaborators who I work with, so this work was definitely not done alone. It was with a lot of help from a lot of different people, as I've listed here. Before we move on to the main part of my talk, I just want to say, why do we bother studying dust in so much detail in so many different forms and structure? So we know, if we sort of look at the life cycle of dust, we know that dust is formed in AGB and RSG stars, then they're ejected to the ISM by planetary nebula. They're processed in the ISM. There's also some thought that dust is also formed in the ISM as well. But once processed, then they incorporated back into star and planet formation. And this sort of makes up this nice life cycle of dust. And it's important to know that dust really only encompasses 1% of the total matter in the universe, but it's really responsible for many key processes within it, such as H2 catalyzation and driving star formation by agglomerating to form planets. And dust, so there's this very cool thing that I find, but it's a massive nuisance to a lot of people who study extragalactic studies, where dust absorbs and re-emits and scatters light, and which we call as reddening. And 50% of the light in the universe has interacted with the dust before it reaches us. So whether we really like dust and enjoy studying it, or whether it's just simply a nuisance that we want to subtract from our observations, we must take it into account. And the only way to really take it into account is understanding its properties and structures properly. And so this sort of leads us into studying the dust density and extinction structure of the universe. And it started all the way with Schlegel et al. A long time ago. And this has led to, which built this really nice 2D dust map using the Kobe Derby data. And from that on, we have decades of really nice work coming up with a lot of 2D extinction maps. But what we quickly realized, the problem with 2D extinction maps is, for one thing, it's two-dimensional. So we don't really see the structure behind this front wall of dust that we have. And also extinction is an integrated quantity. So this means we're really sort of removing structure that would be there by this integration process. So to truly understand what the 3D structure of dust is and what it does, we need the dust density structure. And with that, we can then understand how dust interacts with different forms of gas and processing, and also how the dynamics of galaxies are affected and such. And of course, this leads us very nicely to the fact that we're in the Milky Way, so it's a perfect place to study dust and the 3D structure of dust, especially in the era of Gaia, where we have these beautiful parallaxes with very high precision distances. And oh, sorry, I think there's something wrong with my camera. I'm not sure if you can see things properly. Is my video all okay?
I think so. We are now.
Okay, because I appear stuck on my side. Yeah, I think I'll probably just close the screen there. Okay. Hopefully it's okay now. Yes, so where was it? Yes, so with the Gaia data, we have these wonderful distances and parallaxes from which we then derive the distances. And this makes it very easy for us to study the 3D dust density structure of the Milky Way, because we can then draw extinction values out to hundreds of millions of stars, and we have the distances as well. So from this, we can nicely derive the 3D dust density structure. But then it's deriving the 3D dust density structure of the Milky Way is with a lot of its own challenges, and it's not an easy task to do, because what we want is the dust density, but what we have as a value that's calculated is the extinction, which is the integral of the dust density. So what we have is what we want is a derivative, but we have the integral. So going from this, the integrated value down to the derivative is not a simple task to do. And then another problem is, because we have these, while we do have high precision distance data, they're still not high precision enough compared to the uncertainties we have on RA and DEC. So this leads to this effect called the finger of God effect, which really does need to be corrected. And when I say finger of God, it's sort of these extended line-like structures we see along the line of sight, which aren't actually real. They're simply just an artifactual effect because of these large distance uncertainties. And these need to be corrected for to get the true the density structure of star formation regions, molecular clouds, and the Milky Way itself. And then, of course, density must be positive definite, which means that the integral must always be non-decreasing with distance. But again, this is not easy to achieve because if we just fit to integrate to the integral value, which is extinction, we can't force the derivative value to be positive. And then we then know that clouds are all varying shapes and forms and sizes. We have tubes, we have sheets, we have bubbles inside, we have little blobs. But it's not easy to model these because we're sort of used to modeling these sort of clouds with a single scale length and fixed scale length values, which sort of tends to cause either these very spherical blobs or these very sort of small circle blobs or very large spherical blobs. So that needs to be taken into account as well. And then you sort of try and solve all these problems together in one model. You're talking about a massive increase in both memory and runtime. So it's a very computationally expensive process. So you sort of need to solve all these challenges in one go to be able to do this process. So that's where we worked at in the Gaia group at MPIA for a while now, and we have come up with this wonderful method called Dustribution, which is a tool which is entirely a public tool. It's available online through this website, and the code's available on GitHub to download. All data that we release will also be is also being made public. So what does Dustribution actually do? So Dustribution takes any set of extinctions, distances, and area and depth parameters, and then so of your choice, you can choose any from any catalog that you want to get it from. And then it applies a really nice Gaussian process technique to then build the 3D structure of your, say, a molecular cloud or a star formation region or the whole Milky Way as a whole. And Dustribution is built on a few different very advanced machine learning techniques right now. We use latent variable Gaussian processes, which then help us minimize the finger of God effects and maintain the positive densities. But also with this, we're able to recover all sorts of different shapes and sizes from in the clouds. And then we also use these techniques called variational inference and inducing points, combined with lazy computation, which helps us really increase our memory and runtime. Reduce our memory and increase our runtime. And this means that we are able to map a star formation region like the Orion molecular cloud complex down to about 1 parsec resolution in about half an hour. And the data we use right now to do this is the Foyno et al. Catalog, which actually uses the Gaia DR3 data to mass and WISE to derive extinctions and distances. So before I sort of go into a bit about the results that we derive from Dustribution, I sort of threw a lot of machine learning words out there in my previous slide. So I wanted to explain them a little bit so you have a context on what's happening. So when we see what a latent variable Gaussian process, that simply is a Gaussian process that's built on a layer by layer basis. Because what we have here is our observation, which is our observational extinction. But what we want to get is the density. But then to maintain the positive densities, what we do is we predict our Gaussian process entirely on log density. And then we, from there, go into density, and that gets integrated into our extinction, which then gets compared with the likelihood to get compared to our observation. So really it's just a ladder of processes applied to a Gaussian process to achieve what we want to get. Yeah. And then what does variational inference really do? So with the variational inference, what we do is we replace the target posterior of the Gaussian process with an approximate posterior that's sort of easier to work with and finds the parameters for this approximation, which best produces the true posterior. And then with our sparse Gaussian process, we describe it with inducing points, which then helps us reduce memory. And because with inducing points, we only take a subset of points which represent the whole distribution. And with this subset, we're able to then optimize it much better. And then, of course, we include GPU computing and then use methods such as the torch library and lazy evaluations to further improve our memory. So yes, as I said, Dustribution is a fully public tool available for anyone to use. It's available on our website. We have these very nice visualizations of the star formation regions that we've mapped. And we also have the ability for you to put in your coordinates of your choice, or like a set of coordinates, and you can derive the extinctions and densities to your star formation regions or the whole Milky Way. Yes. So on to our results. So in our latest paper, what we did is we applied distribution to 16 molecular cloud complexes going all the way out to about 2.5 kiloparsecs. So that's the Carina molecular cloud. And so we have built the star formation regions and their 3D structures for Carina, Cygnus, and Cepheus, Cassiopeia, which are some of our larger ones. But we also have some of our smaller ones, which is not very visible here, but we have Perseus and Taurus and things like Canis Major. Yes. And so just building this 3D structure wasn't really sufficient for us because, yes, while we have the 3D structure, we can really nicely see what they look like. And we can get an understanding of what the shapes and sizes of the clouds are. But we really wanted to derive a set of parameters that will describe these clouds really well, and that can then be compared to other data sets. So to do this, what we did was we took the Astrodendro program and did a tiny bits of modifications to make it compatible with our 3D structure. And then this was applied to derive boundary conditions for each of our clouds, and then all the little clouds within giant molecular clouds as well. And we derive parameters such as the sizes, so the L min, L max, and the B min, B max, and D min, D max. We also derive the volumes and filling factors to sort of find out which clouds are more sort of circular, which clouds are more fragmented. And we also derive the masses, which I think is a very crucial value, which then can be compared to values from simulations, etc. And we make these Astrodendro contour structures all public as well, because it would be very interesting in the future, I think, to compare what we derive from these sort of observationally derived 3D structures to simulations, and what simulations derive in their 3D structures. And do we sort of really see these nice shapes and sizes in the simulations as well? So if we sort of take a closer look at some of our clouds that we've derived, so here we have the Orion star formation region. We have the face-on view here, which is rotating, starting from the face-on view. And then we have the top-down view here. And as we can see from here, there's a lot of varying different shapes and sizes that we already see just in this one molecular cloud. For example, one of the nice things we derive is this foreground filamentary structure in Orion, which is visible sort of coming up here. And then we have Orion A very nicely in this sort of triangular flat shape over here. And then if you sort of look at the next slide, where we have California, which is much more of a sheet-like structure. But there's been this long-standing debate, essentially, about the fact that Orion A looks very similar to California on sky. They both have what looks like a bubble structure and a bit of a tail end coming out of it. But then the curious thing is, when you look at it in 2D and then you measure their star formation rates, Orion has a much higher star formation rate than California does. But it's strange because when you look at it in 2D, they all look identical. But we can clearly see the differences here if I sort of flip through between Orion A and California, because while Orion A is sort of smaller and more elongated, California is much larger, and hence, of course, a much larger mass as well. And it's also much more flatter. So you sort of take this larger mass and then the flatness as well as the size and compare it to Orion. It really explains why there's this such a large difference in the dust masses between the two. So that sort of solves this mystery that's out there. And then, so we're looking at the Vela molecular cloud ridge right now. Again, we have the nice face-on view, which is rotating, starting from the face-on view. And then we have the top-down view here. And one of the nice things we see with the velar molecular cloud ridge is that there's a massive distance gradient, which we don't really see again in the 2D view. Should have probably included a 2D view here, because it really just looks like this big blob on sky. So we'd expect it to be this elongated, maybe like a square or something going outwards, but it's not. We see this nice structure and there's a big distance gradient in it. So this really shows the differences that we get when we really map the 3D structure and then look at it from all sorts of different angles. It's very different to what we see and know in 2D. And this really helps us understand things like why star formation rates are different, why we see sort of similarities in some clouds, but then all the other parameters are different. So it is very important to understand the 3D structure to make a real claim about how clouds are different from one another and what drives their characteristics. Yeah, so with all this data that we had, what we did was we wanted to compare it to the Larsons relationship, because it was a simple calculation for us to do. We had our total masses, we had our radii, so we just wanted to see if we take this true 3D sizes into account, what happens to the Larsons relationship. And on the left-hand panel, we have total mass versus spherical radius. So the way we derive the spherical radius here is we take the extent of a cloud in one axis. So here, I think I take the x-axis, and then we assume that's the size in all sides, and then just do a spherical volume, and then hence we have a spherical radius. And then what we do on the right-hand panel is we have the total mass and the true x extent. And nothing really happens to the Larsons relationship. It still holds true whether when we take the true any extent into account as well. So I'm showing the x extent plot here, but I've done it for y and z, and they both all look the same basically. But we have a much larger scatter here, and I think that's mostly because of the uncertainties we have in these extents as well, which contributes to the scatter in all on the dimensions, whereas with the spherical radius, we're assuming this nice spherical volume. And then from there, what we wanted to do was to see, can we see any sort of dust properties with our data? And to do this, we couldn't do it in a 3D format, so we sort of went back to 2D data. So what we did was we took our 3D dust maps to our molecular clouds and then integrated them down, so basically flattening them essentially, and then deriving an extinction map. And so the extinction map that we have from this optical data is a very good proxy for the dust opacity in the optical. And then what we then go and do is take the Planck maps, and specifically the Planck tau at 365 gigahertz, which is an ideal proxy for the opacity, the dust opacity in submillimeter. And then we derive the ratio of the two. And so in contours here, what we have is the distribution contours that we derived. And what we can really see is there's a massive difference in the dense regions of the molecular cloud versus the diffuse regions. So this gives us a hint of the fact that maybe the grain sizes are varying between the dense molecular cloud regions and the diffuse ISM. And we've done this at a parsec resolution for the first time, whereas this has been shown on a much larger scale, but on this very high resolution scale, this is the first time we've shown it. So this leads me to our current ongoing work, actually, and this map will be released very soon in a couple of weeks, and I'm very excited to present this map. It's the first time I'm doing it. So we have derived the full Milky Way out to 3 kiloparsecs at 1.7 parsec resolution with distribution. So we have these very nice, we have derived we can clearly see all the nice structure of the Milky Way, and it's completely, and we don't see any artifacts on combining or anything like that. So there's no merging artifacts. So we're very happy with this map. And And here we have it at, so we have the top-down view on a slice. So this is just the slice along 0. We have the top-down view. We can very nicely see the dense area going towards the galactic center. And then we can really see the extinctions going where the Wheeler molecular cloud ridge would be, as well as Cygnus leading out. And here we have the 3D dust density more zoomed in. This is a 300 by 300 parsec view of it. And again, this is the slice at 0. And we can very nicely see all these wonderful molecular cloud structure in the inner region so very close to the solar system. And if we sort of compare the two, this really, again, shows a very good example of why we want 3D dust densities versus extinctions when we want to understand the true structure of the Milky Way, because as we can see clearly here, we really derived the we lost all these beautiful structures and shapes that we see in the extinction maps. Oh, yeah. And this really brings me to like Gaia DR3, where we have these wonderful data set now coming that just came out. And I think because we have a much larger data set with DR3, I think we have about 500 million stars already. And combining this, especially with infrared data, is a big priority for us right now. And the plan is what we're hoping to do in the next couple of weeks is, yes, combine our Gaia DR3 with infrared data and derive this new catalog, which will then be put into distribution, and then we'll have a much nicer large-scale view, including using Gaia DR3. But what's very nice with Gaia DR3 already is that you're already picking into some of the dense regions which we really couldn't get into. So here on the right, we have the Cygnus star formation region, and it's a fly through, and we can really see all the little dense regions already with just the Gaia DR3 data included. Yeah. And so the capabilities of distribution doesn't, of course, stop there. Well, it's quite flexible. So with the upcoming Gaia DR4 data, we'll have information for the LMC and SMC, and hopefully distances derived to them much better. And then things like the FAT survey for Andromeda. And using all these, we'll be able to derive really nice 3D structures for not just the Milky Way, but other galaxies as well, starting with the local neighborhood. Yes. So yeah, that sort of brings me to the end of my talk, and I think I'll leave my summary slide up, and I'm happy to take any questions.
Okay, thank you very much. So do you have any questions? Hi, Gaussian.
Hello. So thank you very much, Tavisha, for the interesting presentation. It is nice to see so effective usage of the Gaia results of data. So nice simulations. Thank you very much.
I have a question. By the way, thank you for a very nice talk. It was interesting to hear how this stuff is actually done. I've been certainly studying some of the maps that have come out, but I was interested in a different number, which seems like it should be easier to get, which is that past rendering maps, like the ones from Rosine, have not quite the sensitivity to look. What I'm interested in is it's been proposed that there are chimneys, there are directions that where the soft X-ray background is brighter, that you are seeing out of the into the halo through tunnels in the ISM. But if you look at 21 centimeter, there's a minimum of sort of 1.5 or 2 times 10 to the 20th. And this is a little bit, and the question is, where is that? How far away? old reddening maps are not quite good enough to see 1.5 10 to the 20th or 2 10 to the 20th. But now with the much more accurate distances to the stars, why that's helps quite a lot on getting the reddening numbers. So I would think that you could do better. So I'm wondering about integrated, just the integrated dust maps out to various distances, particularly in these fairly high latitude directions.
Yeah, so I think, like you said, the question is why we can't do better, I think, that's what everyone's trying to achieve. Can we get better? And already getting down to sort of this 1.7 kiloparsec resolution was very difficult.
Right, but I'm not asking for any radial resolution. I just want the integral out to different distances.
Yeah, so I think so that is already being done by quite a few people. So Gaia DR3 actually had a map that came out. It went so it technically is going out to the end of the Milky Way. That's what they sort of put at. So it's fully integrating all the way to the end of the Milky Way. And so it's meant to be a map to be used to subtract the extinction for extragalactic studies. And so we already do have this sort of maps, and it's the full Milky Way. So while I showed the galactic plane, this is meant to be the full Milky Way. And so yeah, so we do have these maps, but I guess I think what you're wondering is why they're not high resolution up further out from the galactic plane. I
don't need high resolution. I'd like to know within a kiloparsec where most of that 2 10 to the 20th is. So if one just had a plot of dust column density versus distance.
At 1 kiloparsec.
Without any, with very low distance resolution required. I want to know, is this stuff at 200 parsecs out of the plane, or is it a kiloparsec out of the plane?
The chimneys, right? That's what you're talking about.
Yes,
are they
right.
Like where they're positioned at? Yes.
Yes.
I don't have a very good answer for that because I haven't looked for them specifically. I've mostly been looking at the molecular clouds, but we do so with these 3D dust maps, you can actually look for them. And 1 kiloparsec is actually a region that's been very nicely mapped already. So we've mapped out to 3 kiloparsecs, and that map is already there, which you can take a look at. But also there's like you mentioned, the Lalamont map, or maybe the Lichen-Ensland map also sort of go out to those. That 1 kiloparsec has definitely been mapped, and it's mapped quite well.
Okay. Well, again, I don't need you've gone through this complicated procedure to get all the derivatives and find high resolution locations. And what I needed was considerably less demanding, which is just sort of the original data. What does the integral versus distance look like at low resolution?
Right. Yeah, so I haven't mapped it at low resolution, but this technique is actually very easy to use on low resolution because yeah, I think you could probably get it done in about half an hour if you used we've made the code all public. So you just have to reduce the resolution and run it, and it should give you the very low resolution sort of scale that you're looking for.
Okay.
Yeah.
All right, and this is in your this website you showed us?
Yes, and it's in our new paper that came out a couple of weeks ago, actually.
Okay.
It's a Manars paper.
Can you?
And that should lead you to the Zenodo as well as the GitHub and the website as well.
Okay.
Yeah.
So that's referenced on the website. We can find the paper there.
Yes.
Okay. Well, thank you very much. Very nice work.
Indeed. I am curious what computational resources are necessary to make those modelings.
Yes, so I used a few hundred GPUs that I had access to from MPIA, and it was used mostly consistently for about 2 days. Yeah, so yeah, a few hundred GPUs with a wall clock time of 2 days. This for the whole Milky Way. But if you're mapping just a star formation region, you need a single GPU for about half an hour. But also the code is fully CPU compatible as well, but you're looking at maybe about 6 hours for a star formation region like Orion on a single CPU.
And here you have those 3 kiloparsecs from the galactic plane, yes? Or
yes, so that is this, that's ongoing work. The map's already built, so I'm writing up the paper for it now. Yes, and that we map out down to 1.7 parsec resolution in all directions. So we don't really, we sort of sacrifice the 2D view and the 2D resolution to achieve the distance resolution.
So do we have more questions?
I have a bit naive question. What do you think the essential contribution of the Gaia DR3? Is it a number of stars available, or accuracy of the distance, or both?
I would say Gaia DR3 sort of came out with a few interesting parameters and such. So the distances didn't change from EDR3 to DR3 because the parallax values did not change. But DR3 was really a value-added product from EDR3, what came out. So we had the radial velocities, I think, was very important, which came out with DR3, because that really let us compare. We mapped the spatial structure, but then we can really then compare the dynamics of what's happening in the star formation regions and the Milky Way with these radial velocity data. So we have a spatial plus a dynamical view of the Milky Way. And I would say also then there was this, so the GSP Fort catalog by René Andrea, which derived the extinctions as well as the metallicities and temperatures for like the entire Gaia catalog. Actually, it was 500 million stars. So I think those two are my favorite products that came out with DR3, and I think they're quite important.
Okay. Do you expect another big progress by the future near-infrared astrometry?
Yes, absolutely. I think because while Gaia is amazing at deriving the parameters for a large quantity of stars, the problem that we're having right now is with the optical data, we're missing the dense regions. And no matter how much you put stars into it, the number of stars increase, you can never still get through to the dense regions to map them. So with infrared data, so that's where the key part happens with infrared data, and why we always try to combine the optical and the infrared data when we try to derive these parameters. It's so that we can get to the dense regions. And with the new upcoming infrared missions, I think it would be really important. And especially, hopefully, I'm really hoping that Gaia Near gets approved. It's sort of in very early stages, and it still has to go for ESA bidding and things. But if it gets approved, that would really add a value added. Like an amazing catalog which can be compared with the optical.
Okay, thank you.
I would like to ask, are those molecular clouds moving with the same speed as the sun, or we will run into some cloud in future?
So the sun is, I think, the quick answer is no, they don't all move at the same speed. And the sun is a bit of an anomaly, right? Because it's just sitting there alone, and it's sitting in this bubble and we don't know how it reached there as well. So no, we wouldn't hit a molecular cloud anytime soon if we sort of look at the speed. So it should be okay.
Okay, good. Very good. Will somebody ask more questions? If no, so thank you again for this nice presentation, and good luck in your future work. I see you are young scientists, and we are very glad that you came with your presentation to our seminars.
Yeah, thank you so much for having me. It was very nice to be here, and yeah, have a good rest of the day.
Okay, thank you.